So this is lesson number 4 for Unit 4. It's kind of a follow-up to lesson 3. We're just going to be doing some more work with the second derivative. Just kind of looking ahead so you can see where this lesson is going to go. It's mostly just entirely examples here. We're going to do a physics story and kind of look at how you can do the first and second derivative with some tables like we've been using. And then we're going to do 4 curve sketching graphs where you'll have the little courtesy graph there, but we'll talk about what you could do if you didn't have that. We're going to look at a polynomial. That'll be our first one. Then after the polynomial, we'll do one with an exponential, getting a little more serious. And then after that, a rational. Okay, that one's going to take a couple of pages, right, where we've got fractions of algebra. And then we'll do a radical, an irrational one, okay, just to see how messy that can get. But it's really just all examples today. And we're going to be following up, like I said, our work with the last video, looking at the second derivative. So here goes. Starting off with a physics story. It says the velocity of a particle is given by that v expression there. I've actually written it out a couple of different ways. One factored, where it might be nice for trying to tear it apart to see when it's 0. And then still a polynomial version that could be great for doing another derivative. Okay, so this is already one derivative down the road from s, right? So v, that is s prime, where s is equal to the position. We're already one derivative deep. And I can look at this and say, hey, you know what? This derivative, this first derivative would be 0 at time 1 and at time 2. So that goes and cuts up my number line. And just like we did with graphs, I can say, hey, nice little cut here. These are t values now at 1 and a t value of 2. This story says we don't get to begin until time 0. So I guess the timeline starts at 0, goes until just before 1. All the times between 1 and 2, and then all the times from 2 to forever. This is exactly like what we were doing over the last couple of lessons where we make a table and we've got a couple of rows in it. Here we're going to be looking at this s prime, this first derivative, which is otherwise known as velocity. And then we can make just some general comments on s, on the position of the particle. Okay, well, looking up here, I do see that we've got a value of 0 for s prime for my first derivative, so I can put those in here and here. And now I would go and do some tests. I would go and test a time somewhere inside this time interval, maybe a time of 0.5. And I can either look here or I can look there, whichever is easiest. Maybe the factored one might be nice, right? I can imagine putting in 0.5. I'd have a negative and another negative that's being squared. That's 3 negatives. Now that leaves me an overall negative answer for s prime, which means that s is going to have to be decreasing, right? If it was a graphing question, I'd say, oh yeah, we're decreasing. Or in the physics world, if your s is decreasing, you could say, oh yeah, you're moving to the left. All right, let's check out a time inside this interval, maybe like 1.5. I might go to the factored version. 1.5 minus 1 is positive, and then 1.5 minus 2 is negative, but it's getting squared. So s prime, the velocity, has to be positive, which means that s would have to be increasing. And if your position is increasing, or to say that another way, if your velocity is positive, you have to be moving to the right. And then finally, a time like, say, I don't know, 3 for a time in here. If you try out a time of 3, go to the factored version, 3 minus 1 is positive, 3 minus 2 is positive. You have got a positive velocity, positive derivative of s, which means that s is increasing, or you could say, hey, you're moving to the right. Okay, let's talk about the graph of s. Just kind of thinking about what the graph of s would look like. If we've got a negative derivative switching to a positive, you have to have a minimum position going on. And then this is actually going to be some sort of weird inflection point. You're actually briefly stopped, and then you start up again. Okay, so some questions we could answer now based on that derivative of s, based on velocity. When are you stopped? Oh, yeah, I can answer that. You're stopped at time 1 and at time 2. The wheels are not rolling. When are you moving to the right? Well, I'm moving to the right in this time period between 1 and 2, and also after 2, out to infinity. any extremes in position, where you're like really far to the right or really far to the left? And I would say, yeah, we're going to have a local minimum in your position at t is equal to 1 second. I can see that because of the derivative switching negative to positive, right? I'm eyeballing this transition right in there. That's what tells me it's a minimum. Okay, well, that's the first derivative. That's everything I can do with the physics story. Let's try the second derivative out. So I'm going to work with this polynomial version. I think it would be way nicer to play with this when we go to do another derivative, instead of doing that weird product that we've got there. So my derivative of that would be 3t squared minus 10t plus 8, which does factor, okay, with a little bit of effort. That factors 3t minus 4 and t minus 2. Okay, any times when that is equal to 0? This is our usual game, right? When are those first or second derivatives equal to 0? Yeah, there are a couple. One of them is at time 4/3, and the other one is at time 2 seconds. Breaking up our timeline, we've got all the times from 0 up until just before 4/3, all the times between 4/3 and 2, and all the times from 2 to forever. Okay, checking out acceleration now. Right, that's what this row is, this second derivative. You try a time between 0 and 4/3. I would probably try a time of 1 second. And if you substitute that into this acceleration, into either of these expressions, you'll see that the acceleration is positive. So, what's s doing? What's your position doing? Well, we could just say this. You're accelerating to the right. Then the acceleration goes to 0. So very, very briefly, brief as it is, just for a split second, you're going to coast, okay, just coasting with a constant velocity. Then trying out a time in here, try like 5/3 into those acceleration expressions, and you'll see that the acceleration is negative. So you are accelerating, but you're accelerating to the left. Then at time 2 seconds, you have 0 acceleration, so you're coasting again. And then after 2 seconds, try a time like maybe 3 seconds. Put it into the acceleration expression, and you'll see that you have a positive acceleration, a positive second derivative for s. And so you could say, oh, okay, looks like I'm accelerating to the right. So if we tear apart this whole story, putting both tables together kind of bit by bit, we would actually have quite a few different things happening for this particle. Okay, I've actually got like 7 different stories here. For the first timeline, when we go from time 0, less than or equal to t, less than or equal to 1 second. In that time, both the s prime, the velocity, and the s double prime are doing one thing. And you could say, okay, the particle is moving left, but it's accelerating to the right. So we're going backwards, but accelerating forwards. All right, at time t equals 1, just at that instant, we've managed to finally stop moving left. We are ever so briefly stopped. But if this thing was like a rocket, the rocket engines are still going, and we are still accelerating to the right. So of course it's only a matter of time before you start moving to the right, and that's going to happen for this whole time window from after 1 up until 4/3. One thing is happening in the story. Your rocket, if that's what it is moving to the right, and we're accelerating to the right. So we're picking up speed. Then at time 4/3, just at that instant, We're still moving to the right. After all, we've been accelerating for some time, so we've got quite a bit of speed. But we're going to turn the rockets off. So we're just going to briefly be coasting. Just for a split second. Then, again, just blending the two tables together. From 4/3 up until 2 seconds, one thing is happening in the story. We're moving right, but we're actually firing our rockets in reverse. We're accelerating to the left. And that happens up until time t equals 2. And at that moment, we are stopped. And coasting. The rockets go off. Then, for all of the rest of time, from 2 is less than t, is less than infinity, we're going to do one thing. We're going to be moving right and accelerating right. So just kind of using the same ideas that we've been doing with the graphs, just looking at the two tables, blending the two bits of information together. And we're going to practice that now 4 more times with 4 more different styles of graphs. We're going to do this first one's polynomial, then an exponential, then a rational, and then an irrational expression. And they're going to get messier and messier, just so you know. Okay, this one here, 3x to the 5th minus 5x cubed. First of all, some non-calculus little points here. The domain for this is all reals. Any number is fine going into a polynomial. It does actually have odd symmetry. If you had the courtesy graph, you could see it, or you could imagine putting in a negative x and how you'd actually get the opposite of what you'd have when you put in an x. There are no asymptotes to see. Okay, so none there. Now, let's get into the calculus. What are all the different things that you can do with the first derivative? And this is going to talk about when the graph is, pointing up and when is the graph pointing down, or maybe when it's flat too, right? We can catch that. So the first derivative should be pretty easy with a polynomial. Our y prime would be 15x to the 4th minus 15x squared. And I'm really wondering, well, when is that derivative positive or negative, and when is it 0? So I want to do a little factoring perhaps. So I could say, okay, that derivative could be rewritten as 15x squared, a little GCF factoring, and then an x squared minus 1. And that factors again. This could be 15 x squared, x minus 1, x plus 1. So again, right now you're trying to ask yourself, well, when is it positive? When is it negative? And a great place to start looking at that is, well, when is it 0? Or busted? So we're going to look for critical points. So we're like, okay, could that derivative ever be nothing? Or could it ever be damaged? Right now we're checking for critical points. That's what this test is all about. Well, you can't damage it. It's a nice, beautiful polynomial, so that's a never. But you could make that first derivative equal to 0. 3 possibilities, actually, when x is equal to -1, 0, or 1. So those are some critical x values. Let's go and take our number line, our x values, and let's go and cut the number line up at those 3 spots. That separates the number line into these 4 nice big intervals. And now we can start seeing when is that derivative plus and minus. We already know, based on our work 10 seconds ago, that this derivative is 0 here, and 0 here, and 0 there. We may or may not have some minimums. We're going to have to go and do some checking, right? So we're doing the first derivative test right now. We're going to go and see if that first derivative switches from plus to minus. So we're going to go and pick values inside these intervals, and then we're going to go and test them. You can either test them here, or you can test them there, whichever is easier in your mind. And what I found, you can try this out, just double check me, but I found the first derivative was positive, then negative, then negative again, and then positive. So notice I'm not saying it, right? The AP markers don't like it if you say, it's positive. The derivative is positive, then negative, negative, and then positive, which means the function was increasing, decreasing, decreasing again, and then increasing again. Make sure you don't mix those up in terms of how you say it, right? I want to say for the first column there, the derivative is positive, the function is increasing. I don't want to mix and match and say, oh, well, the function is positive or the derivative is increasing. That's not what I'm trying to say in this part of the work. Now, as I eyeball this derivative and see it make this transition from plus to minus at -1, I know that I have got a maximum occurring for my function. And another one that's happening that's interesting is when that derivative switches from minus to plus right here. That's going to be a minimum. But I don't have a max or a min occurring at x is equal to 0. Turns out it's going to be an inflection point. Okay, and sure enough, right, if I go up to my graph, yep, there is a maximum and there is a minimum. Okay, well, let's see if we can get the bendiness of the graph right, the second derivative. Okay, taking one more derivative, I would work with the simplest possible form, which for me is this one right there, right? Don't work with an ugly product if you don't have to. So working off of that one, that second derivative is going to be 60x cubed minus 30x. And I'm wondering, hey, when are you positive? When are you negative? When are you 0? So I'm going to do a little factoring. That second derivative can be factored with a GCF factor of 30x, and then you would have 2x squared minus 1. And that does not factor nicely, but it could actually equal 0. You know, you could take it aside and say, I'm kind of wondering, you know, could 2x squared minus 1 be 0? Doing a little zero product rule, right? Oh, okay, well, 2x squared would be 1. X squared would be a half. Okay, so plus or minus the root of a half. So yeah, there are some interesting times here for this second derivative. I'm wondering, could you be 0? Could you be busted? I'm looking for potential inflection points, possible inflection points. Now, I don't find any way of breaking it, but there are a couple of ways of making this second derivative equal to 0. I have x is equal to 0 and plus or minus the root of a half. So these are not guaranteed to be inflection points. Whereas up here, these were guaranteed to be critical points. But right now I'm kind of wondering about possible inflection points. Maybe, right? As I go and look at this second derivative to see what it's doing. So I need the table to double check for sure. So I've got some cuts. One cut at negative the root of a half, one cut at 0, and one cut at positive the root of 1/2. Somewhere around like plus or minus 0.7-ish, roughly. Okay, that cuts my x number line up. I've got all the numbers from minus infinity until that first awkward x value. Then from that awkward x value to just before 0, from 0 to that next awkward x value, and then from that last awkward x value all the way out to forever. The second derivative, by our work, we know is already 0 here, here, and here. But are they inflection points? So you test out numbers inside these intervals. You try out some x values very carefully in here to see what happens with your second derivative. And you'll find the second derivative is negative, positive, negative, positive. So the function is concave down, concave up, concave down, concave up. And there are many, many transitions where the second derivative switches sign. Here, here, and here. So these are all going to be inflection points. And sure enough, if you go up to the graph and take a look at all of those 3 points, they're all some nice changes in bendiness. right? So they actually occur around here, there, and about there. Even without that courtesy graph, we could have gone and accomplished that. Okay, so that's as nice as it gets when you're playing with polynomials. We've got 3 more of these to go. They're going to get more serious. The exponential one. The courtesy graph is there. The domain for this thing, can't hurt it. It's all reals. It does not have any symmetry. And for asymptotes, I don't know. I'm not really sure. Maybe, there might be a horizontal asymptote over on that left side, some nice end behavior of y equals 0. We'll see. Okay, let's just do the work with the first and second derivative here and see where that goes. So, for y prime, if I go and try out a derivative here, it's a product rule. I'm going to have 1 times e to the x, and then leave the x, and then the derivative of e to the x would be e to the x. Okay, just going to rewrite that a little bit. If I factor in e to the x out, I would have 1 plus x left. Now, it might look a little nicer to write it like this. X plus 1 times e to the x. Okay, I don't really know much about that, and I'm kind of wondering, could it ever be 0 or busted? Because I also want to know when it's plus or minus. So I'm going to go and check here first. These are possible inflection points. Maybe not for sure, but they're possible IPs. Okay, we're starting to look here. Could you ever make that expression equal to 0? Well, I can see this. Nice binomial. Yeah, how about x is equal to -1? And you can't make an exponential 0, so I think that's it. And as far as busting it, no, that's a never. You can't hurt that thing. So we've only got one interesting number. Oh, I said possible inflection points. I was getting ahead of myself there. My bad. These are critical points. Sorry about that. Okay, so I've got my 1 cut on my x number line at x is equal to -1. That gives me all the numbers before -1 and then all the numbers after -1. And at -1, that first derivative is definitely equal to 0. But what's it doing before 0? And what's it doing after that 0, right? What about before x equals -1 and after -1? So you try a number inside this interval, and you try a number in here. And what you find is the first derivative is negative for the first interval and positive for the next, which means the function is decreasing and then increasing. And since you see this happening, this switch of the derivative from negative to positive, oh, I know there's going to be a minimum at that x value. And sure enough, there is, right there, got a nice little minimum. And if they said justify your answer, I would talk about how that derivative switched from negative to positive at -1. Okay, second derivative. We have to do one more derivative and see how that looks. Trying to find a nice place to start. I would probably start here and do a derivative from that. And as I do, my second derivative, well, of e to the x would just be e to the x. And then moving down the road, there's that story again. Product rule. I'm going to have 1 for the x times e to the x plus leave the x, and then the derivative of e to the x is e to the x. Okay, so yeah, I was working with that little spot there. Let's tidy this up, because that looks pretty messy here. It looks like 2 times we have an e to the x, and then once we have an x, e to the x. I'm going to do a little factoring. I'm going to write that as x plus 2 e to the x. Okay, so now I am looking for potential inflection points when I ask myself, could that ever be 0? Or could that ever be does not exist? So I'm sorry I had that mixed up earlier. Okay, so these are now possible inflection points. We'll have to check and see what the table is doing to know for sure. So could you make the second derivative equal to 0 or busted? Well, yeah, you can make it. You can make it equal to 0 at -2, but you can't bust it. So only one cut to our number line. So here's our x number line, got a cut at -2. And I have all the numbers from -infinity up to -2, and then all of the numbers on the x number line after -2. So you try out a number like maybe -3 into this second derivative just to see whether it's positive or negative. And you find that the second derivative is negative on the first interval, positive on the next. And of course it was 0 here. Since you can see this thing, this second derivative, switching from one sign to another, I know I've got an inflection point happening. Descriptions I can throw at this function, I could say, oh, the graph is concave down and then it goes to a concave up graph. But just watching that second derivative make the switch, I know I've got an inflection point. And sure enough, at -2, yeah, there is this beautiful inflection point there, a little change in the bendiness happening right there. Okay, so that one was our exponential graph. Now we've got two more ugly ones to do. Now we're going to do a rational one. It's going to take a couple of pages, and then an irrational one. Okay, the courtesy graph is there. And let's see if we can start talking about this function. The domain, well, it's mostly okay, but don't go putting in 0 for x. It doesn't like that. It does have odd symmetry. You can see that either from the graph or trying to put in f of -x, and you'll see that there's one negative there. There are some asymptotes. There's definitely going to be a vertical asymptote at x is equal to 0. Right, so that's actually here. It turns out there's actually a horizontal asymptote as well. There's one at y is equal to 0 on either side, like out here and out there. We could watch dominant terms to actually see that. But right now we're trying to work with derivatives, first and second, to see what they show. So this page, let's just do the first derivative. It's going to take us a page. It's a quotient. So derivative of the top, that would be -2x times the bottom left alone, and then subtract, leave the top, and then the derivative of the bottom. But that's not all of it. You then have to take all of that and divide by the bottom squared. Well, that would be x to the 6th. Absolutely worth cleaning these up, right? Because you're trying to figure out when are they 0 or when are they broken, when are they positive, when are they negative, and you can't tell that just from that big mess there. So you start cleaning this up. Looks like we have for our first derivative a -2x to the 4th. And then some foiling here. We're going to have a minus 3x squared and then a plus 3x to the 4th. Oh, we've got a couple of x to the 4th terms, all sitting on top of an x to the 6th. Okay, let's do some more work. This first derivative, just collecting like terms. We're going to have, looks like a single x to the 4th minus 3x squared, all sitting on top of an x to the 6th. Okay, well, we can do some cleaning up here. Factor out an x squared. And I don't really lose any information by canceling out an x squared top and bottom. I don't have to leave any warnings in here because I still have lots of x's down in the bottom there to warn people about not putting 0 in for x. Okay, well, that's my first derivative. Let's go and check for critical points. Are there any places where this derivative, first derivative, is broken or equal to 0, right? So these would be critical points. Okay, well, you could make it equal to 0 if the top is equal to 0. That would mean x squared was 3. So if x was plus or minus root 3, that would do it. And you can definitely bust this one. You can do that if x is equal to 0. Okay, that's 3 critical points, 3 critical x numbers. That's going to cut my number line up into 4 sections. So first row is always my x. I've got one cut at minus root 3, one cut at 0, and one at root 3. So what's left of my number line here? And then from 0 to root 3, and root 3 to forever. I'm doing this because I really want to see when this derivative is positive or negative. From my work already, I know that the derivative is 0 here, 0 at that one, and busted right here. Okay. Now, checking out some values inside those intervals, I have to go test them into that derivative fraction. And after some work, I find that the derivative is positive, then negative again, and then positive. So do I see any interesting little moments here? Well, I've got a switch of my derivative from plus to minus right there, so that's a max. And a switch from negative to positive down in the end here, so that's a min. And the actual function is broken here. And so is the derivative. So kind of not much interesting happening at 0. But we should have a max and a min. And sure enough, if we go and look up here, yep, that's true. There is a max right here, and there's a min. All right. Since we have signs for the derivative, we can go and describe the function with some adjectives here. We can say, hey, the function is increasing and then decreasing. Well, it's decreasing again later on, and the function is increasing. Okay, well, that's only half of this one. Now we have to go and do the second derivative, right? That's what the next page is all about. Let's go look at the bendiness of the graph. Now, I know on this page we're going to do the second derivative, but let me just spend a second and rewrite the first derivative, just so we've got it. We had cleaned it up to here. Now, here we go. Let's do the second derivative. Y double prime. We're looking for the bendiness of the graph now. We want to see what that's going to do. And so we go with the derivative of the top. It's going to be a 2x times the bottom left alone minus leave the top times the derivative of the bottom all over the bottom squared. That would be an x to the 8th. Ugh, messy. I can't look at that and tell you when it's positive or negative or 0 or busted. Not easily. So I want to clean it up. What do we have here? We've got a 2x to the 5th minus a 4x to the 5th plus a 12x cubed. All still sitting on top of an x to the 8th. It's a lot of x's down there. Okay, more tidying. We're going to end up with a negative 2x to the 5th plus a 12x cubed all on top of an x to the 8th. Okay, and do a little factoring. Let's pull out a negative 2x cubed. That leaves an x squared minus a 6 in the top. And also going to be our x to the 8th still down there in the bottom. Well, I think we can get rid of the x cubed. I don't even think we need to leave a warning behind, because there's still plenty of x's down there in the bottom for people to see. All sitting on top of an x to the 5th. Okay, ready to go here. I'm wondering, second derivative, could you ever be 0 or could you ever be busted? So these are now possible inflection points. These are maybes. Okay, in the top. Well, the -2 is not going to do it. It's busy being -2. But you could have a plus or minus √6. That would do it. And down there on the bottom, when x was equal to 0. Yeah, you know what? The function was broken at 0. The first derivative is broken at 0. No surprise. The second derivative and all later derivatives, they're going to be broken at 0 too. So some cuts to our number line, to our x number line here. Got a cut at -√6, one at 0, and one at √6. So my number line breaks here. I go from -infinity to -√6, -√6 to 0, 0 to √6, and √6 to infinity. We know now already that the second derivative is 0 here, broken, and then 0. But now you got to go and test. So you try numbers out inside these intervals very carefully. Try them out in that second derivative fraction. Try them out right here. See what happens. You're trying to see if they're positive or negative. Don't forget that -2, right? It's going to switch the sign on you. And you'll find that the second derivative is first positive, then negative, then positive, and then negative again. So I can now notice that there are some inflection points in here. There's an inflection point here, and there's one here. And then you might ask, well, what about here? The concavity definitely switches. It's not really an inflection point because the graph doesn't even happen there. I like to call it an inflection moment. And if you check out the graph, as we pass through that asymptote, the courtesy graph is on the other side there. It does make a switch, right? In fact, we've got concave up and then concave down before that vertical asymptote, and then it takes that vertical asymptote as an opportunity to switch to concave up. And so it's not really an inflection point because there is no point on the graph, but there definitely is a little inflection moment where it switches around. So -√6, what is that? Somewhere between 2 and 3. You know, sure enough, if you go and take a look on this original graph, yeah, there are some inflection points in there. And there's one, you know, roughly somewhere around here, and roughly one around there. We've got that bendiness of the graph changing. Okay, well that leaves us with one to go. Probably the worst one, to be honest. Let's take a look at what happens with fractions. And you're trying to do this work, this analytic work, and you might not have that courtesy graph. And that's a pretty wild looking courtesy graph. So you're just staring at the algebra, trying to look at it. Like, oh, okay, what about the domain? Ooh, are negatives under the root okay? Oh yeah, sure, it's a cube root, can't hurt it. Plus you're squaring them anyways. So actually the domain for this thing is all reals. It doesn't have any symmetry, and it doesn't have any asymptotes. Well, none of that's calculus. Let's get into the calculus and see what we can do. First derivative. It's not going to be nice. It's a product rule, so we got to go slow and steady here. The derivative of x plus 5 is just a 1 multiplied by the other thing left alone. I'm gonna think of this question, this root here. I'm going to think of that as being x to the 2/3. So I've done my derivative of the x plus 5, and now I multiply it by the x to the 2/3 just left alone. Now, moving down the road, leave the x plus 5, and let's go and do a derivative of that x to the 2/3. So that would be 2/3 x to the -1/3. Now, remember, your goal is to try to figure out, well, when is that positive, negative, 0, or broken? And right now, I have no idea. It is an absolute mess. So I'm going to just start working on this thing and see if I can tidy this up nice and slow here. I have an x to the 2/3 plus. Now, this is some sort of miniature little fraction here. I've got an x plus 5 as well as a 2 upstairs. Kind of looks nice to put the 2 first. And And then down on the bottom, there's a 3 down there from the 2/3. And then this x to the 1/3. Yep, it's down there. Now that x to the 1/3 can't get underneath this first term way out there on the left, but it can get underneath that x plus 5 and the 2. And as I look at that, oh, that looks awful. I need to get one least common denominator here in order to get these fractions together. And in this case, the least common denominator is 3 x to the 1/3. And so this denominator's fine, it's good to go, but we're going to need to raise up this first item, this first term, by multiplying by 3 x to the 1/3 in the top and 3 x to the 1/3 in the bottom. That's just what's required to get our fractions ready to go, and it turns out it actually makes it nice looking. When you do that, you'll now have this common denominator down here in the bottom, which is beautiful, this 3 x to the 1/3. But let's look and see what else have we got. Up here in the top, okay, yeah, there'll be a 3, but then x to the 2/3 multiplied by x to the 1/3, well, that's x to the 3/3. That's just x to the 1. That's just 3x. So it actually cleans up. It starts to look pretty nice. And then here we still have this 2 times x plus 5. Okay, so yeah, that'll be like a 2x plus a 10, right, by the time we distribute that 2. Oh, okay, well, we can keep going with this. Let's tidy this up here a little bit. Looks like we've got a 5x plus 10 up there in the top, and then down in the bottom a 3x to the 1/3. Oh, this isn't too bad. We can maybe factor a 5 out, and we'd have an x plus 2 all sitting on top of a 3x to the 1/3. Okay, I'm looking for some critical points now. Let's go and ask ourselves, is that derivative ever equal to 0, or is it ever busted? And if we're doing this with the first derivative, we are looking for critical points. Well, the only way you can make a fraction equal to 0 is if the top can be made 0, and that does happen when x is equal to -2. And the bottom, yeah, if you made the x is equal to 0. Now, this is neat because the original function at the top of the page is okay if you put 0 in for x. There's no division by 0. It's fine. It's a point on the graph. But now we've got this critical little moment where the derivative doesn't know what to do at x is equal to 0. So our number line gets cut at -2 and at 0, right? These are x values. So we have all the numbers in the world from -infinity to just about -2, all the numbers from -2 to 0, and then all the numbers from 0 to forever. And I know that the derivative is 0 here and broken there. So the derivative is broken, but the function's fine at x is equal to 0. Okay, so you do some tests, and you find out that the derivative is positive here, then negative, and then positive again. So I can actually upgrade these critical points and say, hey, that critical point where that derivative switches from plus to minus, that's a max for sure. And this critical point where the derivative switches from negative to positive, that is a min. It's on the graph. It's going to be a minimum. There just isn't a derivative there. There's no tangent line there. And sure enough, if I go up here, I can see those, right? Yeah, there's a max here. And there's a nice point on the graph. Bit of a cusp, but there's a minimum there. And I can also add some adjectives in here and say, oh, the graph is increasing, decreasing, and increasing. Okay, well, one more page to go. We have got the first derivative sorted out as much as we can. We found critical points, and we found, of those critical points, a max and a min. Now let's go for the second derivative. And just like last time, I'm just going to rewrite the first derivative for a second, just so we've got something to stare at. I'm going to write it like this, actually, 5x plus 10. I think that's a nice way to work, instead of that factored version with the x plus 2, and then 3, x to the 1/3. Okay, here we go, and it's not going to look nice right away. Second derivative. It's a quotient. So derivative of the top, 5. Multiplied by the bottom, left alone, 3 x to the 1/3 minus, leave the top, derivative of the bottom. Okay, what's going to happen? The 1/3 comes down and hits the 3. That's actually kind of nice, but then you'd have x to the negative 2/3, all sitting on top of this bottom squared. Well, that would be 9 x to the 2/3. Okay, I just want to rewrite this to show you how bad it actually is. This second derivative, we would have a 15 x to the 1/3. Okay, that's not so bad. But then here, you'd have minus. This 5x plus 10 is just trying to mind its own business. And then this x to the 2/3 just went running downstairs. But it can only get underneath the 5x plus 10. It can't get over to where that 15 is. And then all of that is sitting on top of 9 x to the 2/3. I don't like that complex fraction, right? This part right here, I find super annoying. So I want to find a way to deal with that. I'm just dissatisfied with staring at it. So I'm going to go and take this whole big numerator. I'm going to give it a little kick with that least common denominator of x to the 2/3. But if I do that to that numerator, I don't want to change its value, so I have to multiply this by x to the 2/3 also. Should make the top look nicer. The bottom might look a little bit messier for a short time. Okay, what do we have? Actually, you know, when this x to the 2/3 distributes and hits here, it'll actually be kind of nice. Because you'll have an x to the 2/3 multiplied by an x to the 1/3. That's just going to be a nice, honest x there. So we have 15x minus, okay, this problem goes away, and you'll just have 5x plus 10. Just be aware of the fact that that 10 is also being subtracted. And then all of that sits on top of, I guess by now it would be 9x to the 4/3 when I add the 2/3 with the 2/3. Okay, well, how much room have I got left? Ooh, not a lot. Okay, tidying up. 15x minus 5x. Looks like we've got a 10x minus a 10, all on top of 9 x to the 4/3. Okay, hey, we could factor a 10 out. No, I'll put it down here. We've got 10 times x minus 1, all sitting on top of 9 x to the 4/3. Okay, time to go and check. Let's go and look for some possible inflection points. I don't know whether these will be inflection points or not, but let's go and look at this second derivative and ask ourselves, could that ever be 0? Could it ever be broken? I don't know. Well, we'll look at the top of the fraction to see when it could be 0. Oh yeah, x is equal to 1. And it will be broken when x is equal to 0. Okay, so 2 cuts to our x number line. 1 at 0, and one of them at 1. I got all the numbers in the world before 0. The numbers between 0 and 1, and then all the numbers in the world after 1. This second derivative is busted right here. So the function was fine at 0. The first derivative was broken and the second derivative is broken. At 1, the second derivative is 0. Then you go and test some values in these intervals. You pick points and you try them out. You would test them right here just to see what's happening. And here's what you find. When you try out a number in that first interval, the second derivative is negative. Then it's negative again, and then the second derivative goes to positive. I only see one time where that second derivative switched sign. So that's an inflection point. This one, not so much. Throw in some adjectives at this story. You could say, oh, the graph is concave down, then concave down again, and then concave up. It's with an inflection point at x is equal to 1. Let's go back to that picture and just add that in. It's a little bit hard to see it, but there is a change in the bendiness of the graph at x is equal to 1 right here. You'd have to use a graphing calculator maybe to see that a little bit better. But it does switch from concave down, a bit of a downward bend, to concave up as you go through that point in there. And that's how you can analytically, without having that graph, go and tear apart the picture and look at that first derivative for increasing and decreasing, and the second derivative for concave up and concave down. And that actually concludes that kind of 4-lesson stint where we were looking at how you can use the derivatives and relate it to graphs.